we're going to Google bioelectronics and we're going to click on the images. So they have soft bioelectronics, smart bioelectronics in healthcare. Advances in soft bioelectronics for brain research and clinical neuroengineering. Ultra-thin material, conductive polymer, hydrogel, nanocomposite. Soft bioelectronics for recording and modulation. Let's click on the link. Advances in bioelectronics for neuroscience and neuroengineering have enabled continuous monitoring of electrophysiological signals and feedback modulation of abnormal brain activities. Despite such progress, there remain issues in terms of long-term high-quality neural interfacing, mainly owing to inherent mechanical, chemical, and electrical mismatches between the device and the brain tissue. New approaches, therefore, are required to address these discrepancies between the biotic and abiotic system. This review introduces the technological advances that potentially solve such issues by using soft materials and devices. Specifically, we summarize recent progress in soft materials, such as nanoscale materials, conductive polymers, functionalized hydrogels, and stretchable conductive nanocomposites. These unconventional materials, combined with customized processing techniques and device designs, provide novel soft device solutions for brain science and clinical neuroengineering. Recent advances in bioelectronics, such as skin-mounted electroencephalography sensors, multi-channel neural probes, and closed-loop deep brain stimulators, have enabled electrophysiological brain activities to be both monitored and modulated. Despite this remarkable progress, major challenges remain, which stem from the inherent mechanical, chemical, and electrical differences that exist between brain tissues and bioelectronics. New approaches are therefore required to address the mismatches between biotic and abiotic systems. Here, we review recent technological advances that minimize such mismatches by using unconventional soft materials, such as silicone/metal, nanowires, functionalized hydrogels, and stretchable conductive nanocomposites, as well as customized fabrication processes and novel device designs. The resulting novel, soft bioelectronic devices provide new opportunities for brain research and clinical neuroengineering. And here's the lovely image that we already looked at. Now let's go back. They have drawing bioelectronics on the skin with tattoos. Let's click on this and give it a read. Monitoring your health by drawing bioelectronics on skin. Engineers at the University of Missouri reported that it is possible to monitor your health by using pencils and paper to draw a bioelectronic device on your skin. The study shows that engineers took a low-cost approach to developing on-skin biomedical electronic devices. Instead of developing on-skin electronics that are typically made by patterning conventional inorganic materials, novel organic materials, or nanomaterials on flexible polymer substrates, which can be costly and complex. The study describes the use of everyday pencils and paper as tools to create cost-effective and disposable on-skin electronic devices, which range from biophysical sensors and sweat biochemical sensors to thermal stimulators, humidity energy harvesters, and transdermal drug delivery systems. The researchers also demonstrated pencil paper based antennas, two-dimensional and three-dimensional circuits, and reconfigurable structures. Many existing commercial on-skin biomedical devices often contain two major components: a biomedical tracking component and a surrounding flexible material, such as plastic, to provide a supportive structure for the component to maintain an on-skin connection with the person's body, said Yan, an assistant professor in the College of Engineering, in a statement. The conventional approach for developing an on-skin biomedical electronic device is usually complex and often expensive to produce, he added. In contrast, our approach is low cost and very simple. We can make a similar device using widely available pencils and paper. And here is this lovely image. You have a sweat sensor, you have a temperature sensor, the energy harvester, and the electrophysiological sensors. The study indicated that pencil-drawn graphite patterns were used as conductive traces and sensing electrodes, while office copy papers were used as the substrate. The researchers found that pencils containing more than 90% graphite were able to conduct a high amount of energy. With 93% graphite pencils, they were able to create a variety of on-skin biomedical devices drawn on commercial office copy paper. The study found that the devices could perform real-time, continuous, and high-fidelity monitoring for a range of vital physiological and biochemical signals, including skin temperatures, electrocardiograms, electromyograms, alpha, beta, and theta rhythms, instantaneous heart rates, respiratory rates, and sweat pH, uric acid and glucose, as well as deliver programmed thermal stimulations. Researchers also discovered that the recorded signals were comparable to those measured with conventional methods. Researchers believe a biocompatible spray-on adhesive could be used on the paper to help it stick better to skin. The next step is to further develop and test the use of the biomedical components, including electrophysiological, temperature, and biochemical sensors. The researchers see broad applications across home-based, personalized healthcare, education, and remote scientific research, such as during the COVID-19 pandemic. These applications range from drawing a biomedical device to monitor a person's sleep levels to conducting research at home. Now let's go back. And we're going to click on this link. Recent advances in bioelectronics chemistry. Research in bioelectronics is highly interdisciplinary, with many new developments being based on techniques from across the physical and life sciences. Advances in our understanding of the fundamental chemistry underlying the materials used in bioelectronic applications have been a crucial component to many recent discoveries. In this review, we highlight ways in which chemistry-oriented perspective may facilitate novel and deep insights into both the fundamental scientific understanding and the design of materials, which can in turn tune the functionality and biocompatibility of bioelectronic devices. We provide an in-depth examination of several developments in the field, organized by the chemical properties of materials. We conclude by surveying how some of the latest major topics of chemical research may be further integrated with bioelectronics. So what do you see here? Biophysical chemistry, electrochemistry and photoelectrochemistry, surface chemistry, and synthetic chemistry. Let's go over here. Organic bioelectronics for in vitro systems. This is for in vitro systems, and because of that, it's available more for the laboratories. So it's there, working with the digital twin, pharmaceutical companies, testing for soil, biomarkers, water, giving them the ability to look in between things more deeply. Bioelectronics are anticipated to play a major role in the transition away from animal studies, offering a much needed technology to push forward the drug discovery paradigm. Now let's go over here to ResearchGate and have a look. They have flexible bioelectronics. Flexible bioelectronics for physiological signal sensing and disease treatment. Design and working principle of flexible bioelectronics. There is your skin, your vessel, your muscle, your bone. There is your brain, your heart, your stomach, your liver, your body. Then you got signal monitoring, circuit, power, substrate, sensor, wireless transmission, cloud storage, dynamic monitoring. This is called intellectual honesty.